Day 16 of 365, and today we're killing a bug that silently times out thousands of LeetCode submissions. You write a clean solution for maximum sum of a subarray of size k. It looks perfect. It passes the small tests. Then on a 100,000 element array, it just hangs. For seconds. Rejected. By the end of these 5 minutes, you'll know exactly why, and you'll have a pattern, fixed sliding window, that turns that timeout into a single, blazing pass. Let's go. Here's the problem cold. You've got an array of stock prices, and you want the highest total over any k consecutive days. The obvious move, for every starting index, loop k elements forward and add them up. 2 nested loops. For our in range, len, prices, k plus 1. Then an inner loop summing prices are through or plus k. That's O n times k. On 10,000 elements with k of 500, that's 5 million operations. Scale it up and your runtime explodes. It's correct. It's just doing the same addition over and over. Now look closely at what's actually wasted. When your window slides from position 0 through 4 to 1 through 5, you recompute the entire sum. But 4 of those 5 numbers didn't change. You already paid for them. The only new information is 1 element entering on the right and 1 element leaving on the left. That's the whole insight. You don't resum, you adjust. Picture a physical frame sliding across a number line. As it moves 1 step, 1 number falls out the back, 1 slides in the front. Let's code the fixed window. First, build the initial window. Window underscore sum equals sum of the first k elements. Set best equals window underscore sum. Now slide. For r from k to the end, window underscore sum plus equals prices at r, then minus equals prices at r minus k. That single line, add the entering element, subtract the leaving one, is the entire trick. Update best equals max of best and window underscore sum. That's it. 1 pass, on, no inner loop. The recompute that cost you k operations per step just became 2 operations, 1 add, 1 subtract. Let me trace 6 numbers so the edges are concrete. Array, 2, 1, 5, 1, 3, 2, with k equals 3. Initial window, 2 plus 1 plus 5 is 8. Slide right. Add prices at index 3, which is 1, subtract prices at index 0, which is 2. 8 plus 1 minus 2 is 7. Slide again. Add 3, subtract 1. 7 plus 3 minus 1 is 9. New best. The window never recomputes from scratch. It just breathes. 1 in, 1 out. Now the real power move. The thing inside the window doesn't have to be a sum. Take anagram detection in a DNA string. Does any k-length window match a target's letter counts? Track a frequency array, int of size 26. Build counts for the first window. Then slide. Increment the incoming character, decrement the outgoing one, and compare against the target. The naive approach resorts every window, which is k log k per step. The frequency array check is O1 per slide. Same skeleton. Enter, exit, but the state is a count map instead of a number. One trap to respect. When your window tracks a product instead of a sum, the enter-exit symmetry breaks if a 0 enters. You can add and subtract forever, but you can't divide by 0 to remove it. So a product window with zeros needs a rebuild, not a tidy divide. The lesson: the data type inside the window decides whether enter-exit is even legal. Sums and counts are reversible. Products with zeros are not. Here's your decision rule, so you leave with a tool, not a trick. The moment you see a fixed length k and consecutive or subarray, reach for fixed sliding window. Then ask what you're tracking: a sum for totals and averages, a max or min for extremes, a count or frequency map for matching and anagrams. Pick the state, write the enter-exit, done. That one question replaces rewriting the inner loop every single time. Day 16 done. The window isn't magic. You already paid for k-1 elements, so only update the 1 entering and the 1 leaving. O1 per step, O in total. Subscribe for day 17.